This screencast will introduce simple linear regression, measures of variation, and will use the unit serviced service call time example to illustrate these measures numerically. We begin with a picture that illustrates some of the quantities we'll define. We assume we have a bivariate data set and will refer to a general data point as the ith data point, xi, yi. The horizontal line is y equals y bar. In the service call time example, this horizontal line could be at the average service call time, y equals 154 minutes. If we only had the y data, that is, we didn't have the x data, our best estimate of a y value would be y bar. If we were to estimate the yi height using the y equals y bar height, the total error that we would make would be this relatively large distance, yi minus y bar. If we squared the yi minus y bar and then summed over all I values, that is I equals 1 to n, all the data points, we would obtain the numerator of the sample variance of the y data. This is a quantity we have previously referred to as SSY, but will now also call SST, the sum of squares total. Now suppose we introduce the x data and the simple linear regression line. Y hat equals B0 plus B1 times x. We can now estimate the yi height with the height of the ith fitted value, yi hat. For this estimate of yi, we have explained y hat I minus y bar of the original total error. If we were now to square each one of these yi hat minus y bar quantities and add them up over all i's, over all data values, we would get a quantity referred to as SSR, a part of the total variation that's been explained by the introduction of the x quantity in the simple linear regression line. For the service call time example, SSR is the amount of total variation that's explained when the number of units serviced in the simple linear regression line are introduced. The rest of the story is the part of the total variation that's left unexplained after introducing the x variable and the least square line. That is, the part left unexplained is the ith residual value, the height yi minus the height yi hat. Squaring the residual values, that is the ei's, and summing over all I, we obtain the sum of square error quantity, SSE. SSE is a measure of the portion of the total error that remains unexplained after introducing the x data and the simple linear regression line. These tables are essentially the tables you completed last time in exercise 2. The data was the number of units being serviced on a service call and the service call times. Here are the x residuals squared added up. 38 is SSX. Here are the y residuals squared added up. SSY is 20,216. Remember, up here we described that SSY quantity or SST quantity as the total amount of variation that exists before we introduce the X variable, in this case the number of units being serviced in a service call variable, and the simple linear regression line. So SST again is 20,216. Here are the products of the X residuals with the Y residuals. When we sum those up, we get SSXY. And here are some quantities we could compute using SSX, SSY, and SSXY. On this table, this column just repeats the number of units being serviced, in this column the service call times. Here are the service call time fitted values. That is, we're plugging in the number of units being serviced and trying to estimate the service call times using the simple linear regression line. Here are the actual service call times. Here are the regression residual values, which always sum to 0. And here are the regression residual values squared. When we add those up, we get SSE is 1,824 units. SSE is the amount of squared variation that's left unexplained after introducing the X data, in this case the units service data, and the simple linear regression line. This next column is new. It's the column of explained variation quantities, the yi hat minus y bars, these guys. Whenever we sum those, we'll get 0. And here are the yi hat minus y bars squared. When we sum those quantities, we get 18,392. That's SSR, our measure of the amount of variation that was explained when we introduced the X variables in the simple linear regression line. Note that when we add up SSR, 18,392, plus SSE, 1,824, we get SST, 20,216. You recall SST was the total amount of variation that existed before we introduced the X variable. The SST quantity was obtained when we summed the squares of all of these relatively larger air quantities. We've pretty much said all of this in what we talked about up here, so I'm going to let you review this, and I'm going to move to the next page. That SST equals SSR plus SSE, that the total amount of squared variation equals the total amount of squared explained variation plus the total amount of unexplained variation is a general result. These quantities are those quantities we saw true for our service call time example. One way to use these quantities is we can compute the percentage of variation that is explained when we introduce the X variable in the simple linear regression line as SSR over SST. After we introduced the simple linear regression line along with the X variable, we had 18,322 units of variation explained out of the original 20,216. That's approximately 91% of the variation is explained by the number of units serviced variable and the simple linear regression line. And we can look at it the other way around too. If we take SSE over SST, there was an amount 1,824 units of variation left unexplained out of the original 20,216 units. That is, we left about 9% of the total variation unexplained when we introduced the unit serviced variable and the simple linear regression line. The quantity that is generally worked with of these two is referred to as r squared, or as the coefficient of determination. It's simply the SSR over SST quantity. That is the measure of how much of the total variation was explained in percentage terms. Like the 91% of variation was explained by the x variable and the simple linear regression line. In simple linear regression, it turns out that the square of the coefficient of correlation equals the coefficient of determination, which explains why they call the coefficient of determination r squared. When the coefficient of determination is exactly 1, that means that the data fits perfectly on a straight line with either a negative slope or a positive slope. For r squared, the coefficient of determination between 0 and 1, the data is more or less scattered. As r squared, the coefficient of determination, approaches 0 or at 0, it says there's no linear relationship between the x and y variables. There are two mean square quantities we'll need in forming an F statistic. The first one is the mean square for regression. It's simply the sum of square for regression, the amount of explained variation, divided by its associated degrees of freedom, in this case 1. Dividing by 1, of course, looks strange, but what that 1 is the number of explanatory, or call them independent variables, that we're using. And in simple linear regression, we always use just one independent variable. In multiple regression, this denominator, this degrees of freedom, will be the number of different types of independent variables we're using. The second mean square quantity is mean square for error, MSE, and we did talk about this at the end of the last class too, is simply the SSE quantity, sum of square error quantity, divided by n minus 2. In multiple regression, this will be n minus the quantity k plus 1, where k is the number of different types of independent variables we're using. And as I said before, in simple linear regression, we're just using one independent, or if you wish, predictor variable. So k plus 1 is 2. We're looking at n minus 2. I've moved to the next page. You might have noticed the quantity MSE is defined the same as the residual variance that we talked about last time, and that's correct. Another name for the mean square error is the residual variance. When we take the square root of the residual variance, MSE, we get the residual standard deviation. The rest of this page involves computing some of the quantities we've just discussed for the service call time example. I'll let you review these items. The next page presents instructions on how to obtain the Excel simple linear regression output. You should open up an Excel spreadsheet and give it a try. You can also use the 2 pages after the next page as a guide to reading the output.